Very good morning to everyone. So, in the last class what we did, we looked into the formulation of Sturm-Liouville problem or a standard eigenvalue problem, and looked into various properties of Sturm-Liouville problem and how the eigenvalues will be evaluated and how the eigenfunctions will be evaluated, and what are the different properties these eigenfunctions will satisfy. So, we have looked into all these aspects. Now, probably we also proved that the eigenfunctions are orthogonal to each other for distinct eigenvalues and they are real. And now, with this background, we will be able to start with solution of any partial differential equation linear and homogeneous with the by the method of using separation of variable. So, what I have done going step by step solution of partial differential equations, first I will take up examples of parabolic equations only, and initially I will be talking about only a two dimensional problem, one dimensional in space, one dimensional in space, another dimensional in time. So, transient parabolic problem. So, we will be looking into basic problems first. So, the basic problem constitutes a problem that we have already discussed in the earlier class. It is a well behaved problem. The problem is that you must be having a set of homogeneous boundary conditions and a non-homogeneous initial condition. That is a well behaved problem, and well posed problem. We will be calling this as a basic problem. So, we will be solving the basic problem in the parabolic partial differential equations for various boundary conditions, and we will look into the solution of this problem almost completely. Next, what I will do, I will take up one problem that will be ill behaved parabolic partial differential equation. That means the non-homogeneity appears in the boundary condition, but the initial condition is homogeneous. So, that we have already discussed in the earlier classes, that it is an ill posed problem. So, we will be looking into the solution of the parabolic partial differential equations of such ill posed problem, and then we will be looking into an actual heat conduction problem, which is basically parabolic in nature. And let us we will just start from the actual problem, and we will make it non-dimensional, and then we will go step by step and follow the same procedure whatever we have done earlier. So, that will be giving the complete picture of how to solve parabolic partial differential equation using separation of variable type of method. Next, I will talk about the multidimensional problem, higher dimensional problem, 3-dimensional problem and 4-dimensional problem. 3-dimensional problem means 2 dimension in space, 1 dimension in time, all these are parabolic, and similarly the 4-dimensional problem means 1 dimensional in space and 1 dimension in time and 3 dimension in space. So, it will be 4-dimensional problem, and we will be looking into the basic problem as well as the complete solution of the problem. So, that completely covers the parabolic partial differential equation in rectangular coordinate or Cartesian coordinate. Then we will take up some of the examples of elliptical partial differential equations and hyperbolic partial differential equations, all in Cartesian coordinate. Then we will move over to the cylindrical coordinate, where you will be dealing with the Bessel functions, and then after at the end we will be moving over to the spherical polar coordinate system, where the eigen functions are nothing but the Legendre polynomials. Once that will be over, then we will be going over to the non-homogeneous partial differential equations and the Green's function method, how to solve them by using separation of variable. So, therefore, for the time being we will be looking into the basic problems only, solution of parabolic partial differential equations, and we will be looking into the solution of the basic problem. Then we will look into the solution of an ill posed problem. Then we will be constructing the complete solution by taking up one actual example of an actual problem. So, we will be looking into the basic problem. First of all, let me define what I mean by a basic problem. Basic problem is an well behaved problem. Well behaved or well posed problem. Okay. So, del u del t is equal to del square u del x square. This is a typically two dimensional parabolic partial differential equation. It is also called one dimensional transient problem. This is one dimension in space and transient means it is time varying. Now, for this problem, if the initial condition is non-zero, non-homogeneous at t is equal to 0, u is equal to f of x, and at x is equal to 0, u is equal to 0, and at x is equal to 0, u is equal to 0. So, that means you have homogeneous and Dirichlet boundary conditions. Homogeneous boundary conditions and non-homogeneous initial condition, then this problem is defined as a well posed problem. Similarly, you can have a Neumann boundary condition anywhere here, but it should be homogeneous, and any Robin-Mix boundary condition may be present, this x equal to 1 at any or of the boundary, and this but that if that condition is homogeneous, then this is a well posed problem. What is an ill posed problem? The ill posed problem is at time t is equal to 0, if you have a homogeneous initial condition, but one of the boundary condition is non-homogeneous, then that will be an ill posed problem. We will be taking over the ill posed problem later on in this class itself. Now, let us look into the solution of the basic problem in parabolic domain, which is a well posed problem. So, if you look into the solution of this, the solution by using separation of variable method, the solution is assumed to be composed of a product of two functions, which one is a function of space alone, another is the function of time alone. So, therefore, but before going into that, we must see when under what conditions one can use separation of variable method to solve a partial differential equation. The basic criteria is that your governing equation has to be a linear one. PDE must be a linear partial differential equation, then only one can think of applying the separation of variable method for the solution. Now, as I said that the separation of variable method includes it assumes the solution u is composed of a product of two functions, one is function of time alone, and is the function of space alone. So, therefore, u is supposed to be a product of function of time and multiplied a function of space only. So, the function capital T is a function of time only and x is a function of space only. So, once we do that, then we substitute this product in the governing equation. So, if you put it in the governing equation, this becomes del t dt dt, and this becomes t d square x dx square. So, therefore, the partial differential becomes total differential, because t is a sole function of time and capital X is a sole function of space. So, next we separate the variables, 1 over t dt dt is equal to 1 over x d square x dx square. Now, if we separate the variables, then if you can look into this equation, the left hand side is completely a function of time alone and right hand side is entirely function of space. So, this is a function of time alone, this is a function of space alone, they are equal and they must be equal to some constant. And we have seen earlier that this constant can have three options, it can be 0, it can be positive, it can be negative, and we have already seen earlier that if this function is 0, if this constant is 0, then we are going to get a trivial solution and we are not looking into that, and if this function is positive, then also we will be getting a trivial solution. That I have proved in the earlier classes. So, this constant has to be a negative constant in order to get a non-trivial solution. So, therefore, 1 over x d square x dx square is equal to minus alpha square. So, minus alpha square ensures that this constant is negative. So, therefore, we multiply both sides by x and bring it on the left hand side. So, d square x dx square plus alpha square x is equal to 0. So, if you remember, if you look into the general value, the general formulation of Sturm-Liouville problem, this equation falls a standard Sturm-Liouville problem under certain modifications. If you remember what is the I will just take a diversion here. So, if you remember what is the standard Sturm-Liouville problem. So, it will be a 0 d square u dx square plus a 1 du dx plus a 2 is equal to minus lambda r u, a 2 u lambda r u. This is a generalized Sturm-Liouville problem or eigenvalue problem. Now, this equation is a special case of Sturm-Liouville problem, because in this case a 0 is equal to 1 and a 1 is equal to 0, okay, a 2 is equal to 0 and r is equal to 1 and lambda is equal to alpha square. Under this condition, the generalized Sturm-Liouville problem boils down to this equation. So, this equation is also a Sturm-Liouville problem. Only thing is that in order to qualify this equation, we have to just check whether the boundary conditions are homogeneous, and we have already known that the boundary conditions are homogeneous in the original problem. So, let us fix up the boundary conditions of this standard eigenvalue problem or Sturm-Liouville problem. These boundary conditions will be obtained from the boundary conditions of the original problem. If we do that, let us look into the original problem. The original problem, the boundary conditions was at x is equal to 0, u was equal to 0. So, it must satisfy the space varying part must satisfy this boundary condition as well, because at x is equal to 0, u is equal to 0, you just put x multiplied by t is equal to 0 and t is not equal to 0, otherwise it becomes a trivial solution. This simply indicates x is equal to 0. So, at small x is equal to 0, our capital X is equal to 0. Similarly, at small x is equal to 1, we have our capital X is also equal to 0. So, therefore, d square x dx square plus alpha square x is equal to 0, subject to boundary conditions this. So, these are the homogeneous boundary condition and this is a standard eigenvalue problem, and we have solved this problem in detail in the earlier class. So, we already know that there are n number of eigenvalues present in this case, and these are equal to n pi, where the index n runs from 1 to infinity, and the eigenfunctions are the sine functions. So, therefore, we can write alpha n is equal to n pi are eigenvalues where n is equal to 1, 2, 3 up to infinity, and the corresponding eigenfunctions are x n is equal to C n sin lambda n x or n pi x. So, these are the eigenfunctions. Now, we can look into the time varying part, that if you look into the time varying part, the time varying part is 1 over t dt dt is equal to minus alpha n square. We just put for corresponding to alpha subscript n, the corresponding solution of time varying part, we just put a subscript n there. So, if we really solve this problem, this becomes dtn tn is equal to minus alpha n square t, or we will be getting the solution as tn, which is a function of time, is nothing but one more constant, let us say C 2 e to the power minus n square pi square t, where alpha n is nothing but n pi in this particular case. Now, we construct the complete solution. If you look into the solution is, if you remember, u was product of t and x. So, for corresponding value for nth eigenvalue, we will be having u n is equal to t n x n, and this will be nothing but C 2 multiplied by C n e to the power minus n square pi square t sin n pi x. Now, C 2 multiplied by C n, it will be a new constant. So, we call that constant as C n prime e to the power minus n square pi square t sin n pi x. So, that is the solution of nth solution corresponding to the eigenvalue nth eigenvalue and nth eigenfunction. Now, as you remember that eigenfunctions are orthogonal functions, and they will be corresponded, and the complete solution will be constituted by summation of all the eigenfunctions. So, I will be getting the overall solution by using principle of linear superposition. Using principle of linear superposition, we can construct the complete solution, and the complete solution will be linear superposition of all these solutions, n solutions, infinite number solutions. So, u as a function of x and t should be summation of u n as a function of x and t. So, n is equal to 1 to infinity. So, we construct the solution summation n is equal to 1 to infinity C n prime e to the power minus n square pi square t sin n pi x. Okay. Now, what is left is, we have got the complete solution almost, but only one constant is not evaluated. We have to evaluate this constant C n prime, and if you remember, there were three conditions on this to define this parabolic problem, two boundary conditions and one initial condition. And if you remember that we have already utilized the two boundary conditions. So, we can utilize the unused initial condition and can evaluate the constant C n prime. If you remember that at x is equal to, at t is equal to 0 for any value of x, u was equal to f of x, that was the initial condition we had, and we have not utilized it till now. Now, we are going to utilize it. So, at t is equal to 0, we put this equation. So, f of x is equal to summation n is equal to 1 to infinity C n prime sin n pi x. So, from this equation one has to evaluate C n prime, and let us see how we will evaluate that. So, what we do? We multiply both sides of this equation by sin m pi x dx and integrate over the domain of x. So, multiply both sides by sin m pi x dx and then integrate over the domain of x. If you do that, it will be f of x sin m pi x dx 0 to 1 is equal to integration n is equal to 1 to infinity c n prime sin n pi x sin m pi x dx and integration over 0 to 1. Now, let us open up this summation, and we can put that we can say that we can utilize the property of orthogonal functions. We have already proved that the sine functions and cosine functions are orthogonal function. That means since the eigen functions are orthogonal functions, so sin n pi x sin m pi x dx from 0 to 1 is equal to 0 for m not is equal to n. So this is the property that we have already looked into, the property of the eigen functions, that the eigen functions are orthogonal functions. Are orthogonal functions with respect to the weight function r. Now, if you remember that just few minutes back we have identified that r is equal to 1 for a Cartesian coordinate in this particular problem. So, if you open up this summation series, then all the terms will be equal to 0, where m is not equal to n. Only one term will survive on the right hand side, that will be for m is equal to n. So, if you do that, you will be getting 0 to 1 f x sin m pi x dx is equal to c n prime integral sin square m pi x, that is m is equal to n dx from 0 to 1. And if you would like to evaluate sin square m pi x dx, let us see what you get. Integration 0 to 1 sin square m pi x dx will be, if you just multiply and divide by 2. So, it will be half 0 to 1 2 sin square m pi x dx. So, if you look into the relationship of sin 2 theta and sin theta, it will becomes sin 2 x is nothing but 1 minus 2 sin square x. So, 2 sin square x will be 1 minus sin 2 x, substitute there. So, 0 to 1 sin square m pi x dx will be half 0 to 1. In place of 2 sin square m pi x, I just substitute 1 minus sin 2 x. So, it will be 2 m pi dx. So, this will be, this is a form of cosine 2 x. So, cosine 2 x is this will be cosine, then 1 minus cos. There is a mistake here. So, cosine 2 x is 1 minus 2 sin square x. So, 2 sin square x is nothing but 1 minus cos 2 x. So, it will be cosine 2 x, cosine 2 pi m x dx. So, carry out this integration. So, half the first one will be 0 to 1. So, it will be 1 minus integration of cosine 2 pi m x is nothing but sin 2 pi m x sin 2 pi m x divided by 2 pi m from 0 to 1. So, half into 1 multiplied by sin 2 pi into 2 pi m divided by 2 pi m. So, sin 2 pi m will be equal to 0, sin 2 pi will be always 0 and sin 0 is 0. So, you will be getting a 0 contribution from there. So, it becomes half. So, integration of sin square m pi x dx is nothing but half. So, therefore, what we will be getting is from 0 to 1 f of x sin m pi x dx is equal to C n prime multiplied by half. So, C n prime is nothing but 2 0 to 1 f of x sin m pi x dx. Now, what we do? We change the running variable m from m to n, change running index m to n. So, we will be getting C n prime in terms of n. So, we will be getting C n prime is nothing but 2 integral 0 to 1 f of x sin n pi x dx. So, that gives me the complete solution that u as a function of x and t should be is equal to n is equal to 1 to infinity C n prime e to the power minus n square pi square t sin n pi x. Okay. So, where the constant C n prime is given by this expression. Now, if the value of f x is known to you, then you can integrate this out analytically, or if f x is a complicated function of x, then this integration has to be evaluated numerically using a trapezoidal rule or Simpson's rule. Now, we will just so this f x can be a constant or in general it can be a function of x. If f x is a simple function of x like x or x square or e to the power x or cosine x k x something like that, then this equation this integration can be solved analytically, otherwise one has to take recourse to numerical techniques. For example, I will just solve this problem for f x is constant. If f x is constant, let us say a 0, let us see what we get out of this equation. So, C n prime is nothing but 2 a 0 integral sin n pi x dx from 0 to 1. So, this therefore, you will be getting 2 a 0 integral of sin n pi x is nothing but minus cosine n pi x divided by n pi. So, it will be from 0 to 1. So, 2 a 0 with a minus sign, it will be cos n pi divided by n pi minus 0. So, it will be cosine 0. So, it will be 1 over n pi. So, you will be getting you can absorb the minus sign inside, it will becomes 2 a 0 over n pi 1 minus cosine n pi. So, the complete solution in this case becomes u x t is nothing but summation of n is equal to 1 to infinity 2 a 0 1 minus cosine n pi over n pi e to the power minus n square pi square t sin n pi x. Okay. Now, if f x is a known function of x, let us say f x is nothing but a linear function a 0 x, and how we will be evaluate this C n prime. The C n prime is 2 0 to 1 f of x sin x. So, it will be a 0 x sin n pi x dx. So, therefore, 2 a 0 will be taken out and this will be x sin n pi x dx. So, we carry out this integration by parts. They take this as the first function, this is the second function. So, first function integral of second function will be minus cosine n pi x divided by n pi from 0 to 1 minus differential of the first function, differential of first function is 1, integration of second function minus plus cosine n pi x divided by n pi dx from 0 to 1. So, it becomes 2 a 0 minus 1. So, it will be cosine n pi divided by n pi, and when you put it 0, the whole term becomes 0. So, we just evaluate this one. So, integral of cosine n pi x is nothing but sin n pi x divided by n pi from 0 to 1. Okay. So, this becomes 2 a 0 minus cosine n pi over n pi plus 1 over n square pi square, sin n pi is 0 minus sin 0 is 0. So, the whole contribution becomes 0. So, you will be having minus 2 a 0 over n pi cosine n pi in this particular case. So, if you look into the complete solution, I am just writing it over here. The complete solution is given as u as a function of x and t. This becomes minus 2 a 0 summation n is equal to 1 to infinity cosine n pi divided by n pi e to the power minus n square pi square t multiplied by sin n pi x. So, that gives the complete solution for this particular case. Similarly, okay, so there is yeah, so it will be 0. This is fine. This is a perfect solution. This is a correct solution. So, similarly, if you have another function of f x is a known function, let us say a 0 x square or 2 x square or x cube, or let us say e to the power k x, something like this, the C n prime can be evaluated by integration by parts, and you can construct the complete solution. On the other hand, if f x is a complicated function, like where the numerical the analytical solution by using separation by using the integration by parts is may not be possible. For example, a case like f x is equal to a 0 x square plus divided by 1 plus 3 x to the power 3 raised to the power 5. If it is a complicated function like this, one cannot do the integration by parts, one has to do one numerical integration to evaluate this integration of f x integration 0 to 1 f x sin n pi x dx. That integration has to be evaluated numerically in one step. So, a numerical integration is required, maybe using trapezoidal rule or Simpson's 1/3. So, whatever the method, one can take recourse to solve this problem completely. So, that completes the solution of basic parabolic basic problem with a Dirichlet boundary condition. Next, we will be taking up a parabolic basic problem in case of Neumann boundary condition, parabolic basic problem for Neumann boundary condition. So, this problem will be something like this: del u del t is equal to del square u del x square. At t is equal to 0, we have u is equal to f of x, and at x is equal to 0, you will be having del u del x is equal to 0. At x is equal to 1, you have u is equal to 0. Now, only one non-homogeneity is present in the governing equation. So, therefore, but this boundary condition is a Neumann boundary condition. So, again we define this problem by using separation of variable. So, u has to be a product of two terms, one is assumed to be function of x alone, another is a function of time alone. If you substitute in the governing equation, this becomes 1 over x, this becomes x dt dt is equal to t d square x dx square. So, this becomes 1 over t dt dt is equal to 1 over x d square x dx square. So, again the left hand side is a function of time, only the right hand side is function of space only, and they are equal, they must be equal to some constant, let us say. So, this will be some constant. Now, again this constant can be 0, can be positive, can be negative. We have already seen if this constant is 0, that in the earlier class we have proved if this constant is 0, it will be giving a trivial solution. For positive also it will be giving a trivial solution, but if it is minus alpha square negative, then it will be giving a non trivial solution. So, let us do that. So, 1 over x d square x dx square is equal to minus alpha square. So, you will be having 1 over d square x dx square plus alpha square x is equal to 0. Now, let us construct the boundary condition of the x varying part. The boundary condition of the x varying part must be satisfying the boundary condition in the space of the original problem. So, if you look into that equation, at x is equal to 0, you had del u del x is equal to 0. Therefore, you just put x u is equal to x into t, t is independent of x. So, you will be getting dx is equal to 0. So, it will be a total derivative, because capital X is a sole function of small x. Similarly, at x is equal to 1, we have u is equal to 0. So, therefore, your capital X must be equal to 0. So, again we will be having a homogeneous boundary condition and a standard form and a special form of generalized Sturm-Liouville problem. So, this is a standard Sturm-Liouville problem or standard eigenvalue problem with the homogeneous boundary conditions. We have already solved this problem solution to we have already looked into the non-trivial solution for this particular problem in the earlier class, and we have seen that the eigenvalues will be constituted by 2n minus the alpha n, and the eigenvalues they are 2n minus 1 pi by 2, where n is equal to 1, 2, 3 up to infinity. So, these are the eigenvalues to this problem, and the corresponding eigenfunctions are given by the cosine functions. We have already seen this in this case the Neumann boundary condition, the eigenfunctions are cosine functions, and x n is corresponding nth corresponding to nth eigenvalue, x n is the corresponding nth eigenfunction. So, this will be C 1 cosine alpha n x, where alpha n is nothing but 2n minus 1 pi by 2. Okay. So, we construct the nth the u n, the solution for nth eigenvalue and eigenfunction. So, this will be nothing but T n multiplied by x n. So, therefore, it will be and if you look into the solution of T n will be nothing but exactly how the same way we have done earlier. This will be C 2 e to the power minus lambda n alpha n square times t. So, therefore, if you multiply T n and x n, it will be C 1 into C 2. So, it will be a new constant. Let us say new constant is C n. It will be e to the power minus alpha n square t cosine alpha n x, where alpha n is given by this expression. So, now this is the nth the solution corresponding to nth eigenvalue. So, we can linearly superpose for all the eigen solution, and we can construct the complete solution. So, let us construct the complete solution. The complete solution will be summation of u n. So, therefore, this will be nothing but n is equal to 1 to infinity C n e to the power minus alpha n square t cosine alpha n x. Now, we have all so we have utilized the two boundary conditions, and only one constant is left to determine and completely specify this problem. So, therefore, we have to use the unused initial condition of the original problem to solve this problem. So, therefore, if you remember the initial condition at t is equal to 0, u was equal to some known function of x. So, we put it there. So, this becomes f of x should be is equal to summation C n cosine alpha n x n is equal to 1 to infinity. Again the eigen functions are orthogonal to each other for a Sturm-Liouville problem, and we have already proved it earlier. Therefore, the orthogonal properties of cosine functions we can use. These are integration of cosine alpha n x, cosine alpha m x dx is equal to 0 for m not is equal to n. So, for m not is equal to n, cosine alpha n x multiplied by cosine alpha m x dx is equal to 0, where alpha n and alpha m are two distinct eigenvalues. So, therefore, if we multiply both sides by cosine alpha m x dx and carry out the integration from 0 to 1 and see what you get. So, we multiply both sides by cosine alpha m x dx and carry out the integration over 0 to 1 domain of x. So, n is equal to 1 to infinity C n integration cosine alpha n x cosine alpha m x dx from 0 to 1. Now, for alpha n, now if you open up this summation series, all the terms will vanish when alpha m is for m not equal to n, only one term will survive, which one is m is equal to n. So, this becomes C n 0 to 1 cos square alpha m x dx. Now, if you evaluate this integral 0 to 1 cos square alpha m x dx. So, if you remember the expression of cosine 2 alpha m x, cosine 2 alpha m, you just divide it by half from both sides. So, it will be half 0 to 1 2 cos square alpha m x dx. So, you utilize the identity cosine 2 x is nothing but 2 cos square x minus 1. So, utilizing this identity, we can substitute this 2 cos square alpha m x as 1 plus cosine 2 alpha m x. So, if you do that, what you will be getting is that integral 0 to 1 cos square alpha m x dx is nothing but half 0 to 1 1 plus cosine 2 alpha m x dx. So, carry out this integration, this will be half plus half integral of cosine 2 alpha m x dx 0 to 1. So, this becomes half plus half, it will be sine 2 alpha m x divided by 2 alpha m from 0 to 1. So, it becomes sine 2 alpha m is nothing but 0, and this will be sin 0 is also 0. So, you will be getting half. So, integral cos square alpha m x dx is also half. Okay. So, what we will be getting is that the final form is f of x is so C n will be okay. So, C n will be nothing but 2 times 0 to 1 f of x cosine alpha m x times dx. Again, like the earlier case, what we have done in the earlier case, in case of Dirichlet boundary condition, the alpha for a known function of f x, we can evaluate this the expression of C n completely, and you will be getting an analytical solution. For if it is constant, you can evaluate it analytically. If it is a simple function of x, we can evaluate it analytically by using the integration by parts, and if it is a complicated function, then we have to take recourse to numerical technique and we have to carry out this integration probably numerically. So, therefore, I will just solve this problem for constant value of f x. For f x is equal to a naught, this C n will be 2 a naught integration of cosine alpha m x dx, and this becomes 2 a naught sin alpha m x divided by alpha m from 0 to 1. So, this becomes 2 a 0 sin alpha m divided by alpha m. So, what you get is that C n becomes 2 a 0 and we put the value of alpha m as 2 n minus 1 pi by 2. So, this becomes 2 m minus 1 pi by 2. So, pi is there, 2 is there, and this will be sin 2 m minus 1 pi by 2. Change the running index m to n. So, you will be getting C n is nothing but 4 a naught divided by 2 m minus 1 pi sin 2 n minus 1 pi by 2. So, in this particular case, that is the expression of sine. So, you will be getting complete solution as u as a function of x and t is 4 a 0 in summation n is equal to 1 to infinity sin 2 n minus 1 pi by 2 divided by this is 2 n, okay, 2 n minus 1 times pi e to the power minus lambda n square t cosine lambda n x, where lambda n is 2 n minus 1 pi by 2. So, that gives the complete solution if the function f x is equal to the constant a 0. If it is a known function like x, x square e to the power k x sin k x cosine k x or whatever. So, then that integral has to be evaluated by parts. If it is a complicated function, as we mentioned earlier, one can use the numerical technique to evaluate that. So, that gives the complete solution in case of Neumann boundary condition of parabolic partial differential equation. Then we look into case number 3, where we deal with a parabolic PDE of a well posed problem with mixed boundary condition. If you do that, the problem is something like this: del u del t is equal to del square u del x square, subject to at t is equal to 0, u is equal to f of x at x is equal to 0, you have u is equal to 0, at x is equal to 1, you have del u del x plus beta u is equal to 0. So, again this problem has the homogeneous boundary condition and non-homogeneous initial condition. So, it is a well behaved problem. So, we can and it is a linear partial differential equation. So, we can use the separation of variable type of method. So, u is assumed to be a product of two function, one is completely a function of time, another is completely a function of space. So, if you substitute this there and separate the variable, what you will be getting is 1 over t dt is equal to 1 over x d square x dx square. The left hand side is a function of t only, the right hand side is a function of space only, and they are equal. So, they must be equal to some constant. Again this constant can be 0, can be positive, can be negative. We have already seen that for 0 and positive value you will be getting a trivial solution. So, therefore, in order to get a non-trivial solution, this constant must be equal to minus, it must be equal to negative. So, it will be, if you look into the solution, so this becomes d square x dx square plus alpha square x is equal to 0. So, this is again a standard eigenvalue problem or Sturm-Liouville problem. Now, we have to see whether the boundary conditions are homogeneous or not. They are. At x is equal to 0, your original boundary condition was u equal to 0, therefore, capital X must be equal to 0 there. The space varying part must be satisfying the space varying boundary condition, the space varying part must be satisfying the boundary condition of the original problem in space. So, at x is equal to 1, you had del u del x plus beta u is equal to 0, put u is equal to t into x. So, this becomes at x equal to 0 dx dx plus beta x is equal to 0. So, you have the standard eigenvalue problem with homogeneous boundary conditions. So, this it can be solved, and if I remember, the eigenfunctions are given by the by sign functions, and eigenvalues are given by the roots of a transcendental equation, but I do not remember the form of the transcendental equation. Let us derive that. So, solution of this will be x is equal to C1 sin alpha x plus C2 cosine alpha x. Solution is composed of the combination of sine and cosine function. If you put the first one, x is equal to 0, C1 sin 0 is 0. So, this becomes C2 cos 0 is 1. So, C2 equal to 0. So, therefore, the eigenfunctions are nothing but the sine functions C1 sin alpha x. Now, we put the other boundary condition dx dx. So, it will be C1 alpha cosine alpha x evaluated at x is equal to 1 plus beta x. X is C1 sin alpha x. So, C1 sin alpha x evaluated at x is equal to 1 should be equal to 0. So, therefore, C1 alpha cosine alpha plus beta C1 sin alpha is equal to 0. So, divided by sin alpha. So, what you will be getting is C1 alpha tan alpha plus beta must be equal to 0. For in order to get a non-trivial solution, C1 must not be equal to 0. So, C1 cannot be equal to 0. So, the solution is alpha tan alpha plus beta must be equal to 0. So, this equation has infinite number of roots, each and every root is the eigenvalue of the particular problem. So, we write the root by n. So, the index n runs from 1 to up to infinity. So, eigenvalues alpha n are roots of this roots or zeros of this transcendental equation. These roots can be evaluated numerically and one can get those values. So, corresponding eigenfunctions are sine functions. So, we can get the time varying part as earlier we have seen that Tn is minus lambda n square t dt. So, integrate it out. So, you will be getting Tn is equal to some constant times exponential minus lambda n square t. And if you look into the time varying the space varying part, the corresponding to nth eigenvalue x n is nothing but C1 sin alpha n times x. So, we can construct the nth solution corresponding to nth eigenvalue is Tn x n. We multiply these two C1 and C2, it will be giving a new constant. So, this will be Cn sin alpha n x exponentially minus this is alpha n, right. This is not lambda, this is alpha. So, it will be having alpha n square t. Okay. So, I stop here at this class and in the next class I will be completing this problem. I will be taking up this problem from this point onwards and complete this problem completely. Okay. So, we will be moving forward how to solve the ill behaved problem. Thank you very much.